Welcome to the Innovator Spotlight, a podcast featuring conversations with some of the most innovative leaders, designers, and technologists in biomedical engineering and the health sciences. I'm Sean Grace, and today's guest is Dr. Ronke Olabisi, Assistant Professor in the Department of Biomedical Engineering at UC Irvine, where her research focuses on tissue engineering, wound healing, and regenerative medicine. Dr. Olabisi is the recipient of multiple awards, including a 2018 NSF Career Award and a 2019 Johnson & Johnson Women in STEM and Design Award. In 2019, she was named one of the Biomedical Engineering Society's Young Innovators in Cellular and Molecular Bioengineering. Dr. Olabisi is a member of 100 Years Starship that seeks to replicate the rapid technological development stimulated by the moon landings by tackling human interstellar travel. Ronke is also an accomplished sword fighter and led many of her collegiate fencing teams to victory. She is speaking with us today from her home in Santa Monica. Hi, Ronke. Thanks so much for joining me today.
Hi, thanks for having me today.
It is my pleasure and my honor. So, fencing. Tell me more about that.
I love fencing. Right now, everybody keeps sending me these memes, how it's the best COVID sport, because if anybody gets too close to you, you stab them with a sword, you
Right.
wear a mask at all times and gloves, and I can't argue with that. It is pretty good COVID sport.
I would say might be the perfect COVID sport.
Right? So I started fencing when I was an undergrad, and actually when I was an undergrad, women could only fence one weapon. And there are three weapons in fencing, and one is the foil, the other is the épée, which what people think of when they think of like the Three Musketeers. And the final one is the saber, and the saber is the only slashing weapon.
Hmm.
And when I got to grad school, I tried the saber, and because of Title IX, if you don't allow women to have their own team, you have to let them be on the men's team, and there was no women's team, and so I joined the men's team, and I had initially been the captain of the foil team for the women, and after I started trying saber, I just really loved it. And the women's team, we elected our captains. The men's team, it was a fight to the finish. So I was captain of the men's team in saber when I was in grad school.
Incredible. Don't mess with Ronke. I'd love to hear about what you're working on at your lab at UC Irvine. Can you give us an overview?
So I do wound healing, and I developed a system that can heal wounds, and it looks like it heals it without scar. It looks like it heals it faster than your wound would normally heal. It was in a diabetic model. I also do bone formation, where I'm trying to precisely control where bone will form, because right now bone morphogenetic protein is one of the growth factors that they use to grow bone when they're trying to do fusions. And there are a lot of bad side effects. Like some people have bone growing into their spinal canal, and it can cause problems with breathing. It can cause neurological impairments, things like that. And what I've honed in on is nacre, which is mother of pearl. And one of the things that's really cool about it is I want to say 1931, they discovered this jaw that had these three nacre teeth in it, and it was a Maya jaw. And, the archaeologists assumed that they put the teeth in so that the person could be buried whole and pretty. And it sat in this museum until in 1972, a dentist looked at it, and his name was Dr. Bobbio. And he thought to himself, that looks too good to be postmortem. So he asked if he could x-ray it. And he was right. And they had done this in a living person, and they had osseous integration into that bone, which meant they had tooth implants better than what we have today. Those
Wow.
teeth did not come out. It was the 7th century. So they didn't come out for thousands of years. You're always hearing about how tooth implants are failing now,
Right.
right? So the Maya did it way back in the day. And, because of those results, a lot of people really started looking at nacre, and since then, it's been called an implant material of unparalleled virtues. And, this French group, they put they ground up some nacre and they combined it with blood, and they made a putty, and they used it to repair maxillofacial defects in people. People have put it into sheep, into mice, into dogs, and it just does not cause an immune response, and it really incorporates nicely into the bone. And so what I wanted to do is I wanted to see if I could use nacre to control where bone forms. And we recently did that, and our paper is now submitted and in review, and hopefully the results will come out soon.
Is there a synthetic nacre, or does it have to be organic?
So nacre is made of a polymorph of calcium carbonate called aragonite, and you can have synthetic or geologic aragonite, but the nacre that seashells form is 3,000 times stronger, and it's 3,000 times stronger because the proteins lay it down in what they call a brick and mortar structure. So they'll have these nano-sized pieces of aragonite that are arranged in it. I mean, it really, when you look at an SEM image, if you Google it, it looks exactly like brick and mortar. That it's very organized and very laid down, and it's this structure that makes it 3,000 times stronger than geological or aragonite.
So what got you first interested in bones?
So for as long as I can remember, I've wanted to be an astronaut. And so I was in the aerospace department, and I was taking a composites class. And the professor there said, I want you guys to design a material for a non aerospace application. And I was at a loss. I went on the internet and I hunted through pictures, and I kind of have like a morbid streak. And I saw this picture of a hip implant, and it had broken through the bone. And I just went down a rabbit hole where I kept looking, and I was like, "Why did this happen?" And I discovered something called stress shielding, and in stress shielding, the bone decides, so the implant is taking up too much of the load, and the bone is not feeling the load that it normally feels, and the bone decides, "Well, why am I here? I'm gonna optimize myself away." And so it really resorbs itself, and that's why that person had that broken, the hip had broken through.
Mm-hmm.
And as a mechanical and aerospace engineer, when I studied materials, we just cycled them until they failed, and they all pretty much you could predict how they would fail. And bone was so interesting to me. It was dynamic. It would optimize itself better than the optimization software that I used. It would grow more if it needed to. And I fell in love with bone. And I was like, okay, I guess I'm a biomedical engineer now.
So you said that the bone is dynamic in
Mhm.
its healing processes or its generation or regenerative process. What's the feedback loop there? I mean, how does it know what its stress level is going to be or what it won't be in order to design itself to be properly tuned?
So, no matter how old you are, you could be 90 years old. Your skeleton is only at most 10 years old. And
Is
the
that
reason
right?
is yeah. So if you
Huh.
think about it, like if you take a soda can and you take that tab and you bend it over and over and over, it's gonna break. And the
Mm-hmm.
same would be true of your bones, right? So they would be cycled repeatedly throughout your lifetime, and they would just break.
Mm-hmm.
And so to prevent that from happening, there's this constant turnover where the tiny little wear is eaten up by these cells called osteoclasts, and they eat up bone. And that it's rebuilt in the same spot by osteoblasts, and they lay down bone. And osteoblasts, they're these cells that will also trap themselves. And so they'll build up bone all the way around themselves until they've kind of cemented themselves in the center. And then these cells become what's called osteocytes. and they talk to each other. So they've got these little projections where one cell is talking to another cell, and they believe that these cells are the ones that detect strain, and they'll tell, "Okay, you need to grow some more." "Okay, I'm gonna grow some more," or, "Okay, you need to not grow as much." And so it's this communication between these entrapped cells and this strain. They respond to strain, and they give a signal out to all the other osteoblasts to build or to not build. And it's just this beautiful process. It's this dynamic, wonderful optimization process that I fell in love with.
Now, you mentioned that your very first dream was to be an astronaut. Was that also your first academic path, aerospace?
So I started in aerospace, and I switched because there was this really fascinating design competition that MIT had, and where you got to build robots, and I really wanted to build some robots. And so when I went back
Mm.
to grad school, I then switched again, and I got into aerospace engineering again. And it's all, when you're young, you think you have to be an aerospace engineer to be an astronaut, which is not true. Um, and
Hmm.
so
I
I
would think that.
yeah, I did, young me thought that. But then
Hmm.
I realized, that most astronauts were not aerospace engineers, so I just started following what I loved, and,
What are most astronauts, by the way?
I think most of them, they're military astronauts, there are doctor astronauts, and they're mechanical engineer astronauts. Well, the science astronauts. But of all of the engineers, there are more mechanical engineer astronauts than aerospace engineering astronauts.
Hmm.
I think for the longest time, the most of them were military, and then they opened it up to civilians.
So tell me about 100 Year Starship. What is that project? What is that project all about?
So it's every time we talk to physicists, they're like, "That's impossible." And, yes, right now it is. But if you think about it, we went to the moon in 1969. In 1869, if you had told everybody going to the moon is impossible, you would have been correct. But if you think about, like, all of our technology today, you can't separate how much has been sparked by the space program. And so we have water filters because they needed to figure out a way to recycle water for the Apollo astronauts. So they developed water filters.
Hmm.
We have GPS because of NASA, because they made communication satellites so they could communicate with the astronauts.
Right.
They needed to have drills so they could drill moon rock and bring moon rock back, so they invented cordless drills.
Hmm.
All of these things that are like, there is a website that you can go to on NASA where you can look at how everything in your world is derived from the space program. Now, if you think about, we only took 9 years to decide to go to the moon and then get there, yet our entire technology is impacted by that trip. What would our technology look like if in 1869 we decided to go to the moon? And so if you think about it that way, it's more of a thought experiment. So if
Right.
I
Right.
need
Right.
to go to another star, what are the kinds of things that are going to help me? Well, I need better energy. Well, yeah, that's going to help the Earth too. What else is going to help me? I probably would benefit from some sort of way to put people into suspended animation, and that would help people who have diseases or sicknesses in some way, or injuries that require that you put them out until the expert. Like if I have an inoperable brain tumor that only 2 people in the world can do, and it's gonna kill me, if you can put me in suspended animation, that's gonna help a lot of patients on the Earth.
So
There
explain suspended animation. I mean, it's certainly a term that most of us are familiar with. However, I'm not sure how many people fully understand what it really means. How do you define suspended animation?
Well, in science fiction, you're just frozen and then rewoken up.
Right.
There are a lot of researchers who are investigating torpor, which is kind of a certain type of hibernation. And so, I mean, we have hibernating animals, and we have researchers that are looking into ways to make non-hibernating animals hibernate. And if you could do that with people, can you imagine like putting you in hibernation so that you could slow the spread of your cancer? Putting you in hibernation, so that the treatment worked in a better way. There are a lot of things that it could be applied for, and a lot of things that we don't necessarily know. Like, when lasers were first invented, a lot of people were like, "What good is this?" And then, you use it to scan all your groceries in. You use it to for CD players. We've used it for so many things that it's been
Right.
useful for that people didn't. I mean, I know a lot of, architects and builders who use it just to measure things very quickly.
Right.
And so you can envision a lot of applications, but then there would be a lot of applications that you didn't even envision. And I it's when you're, trying for a goal that you have never tried for before, those are the things that bring innovation in a way that we can't necessarily when we're just, like, looking at because obviously having a water filter helps a lot of people in developing countries that don't have access to clean water, but it wasn't invented until the space program needed it,
Right.
right? And so there's so many, like, recycling in so many fundamental ways wasn't really on the radar of people in the '60s as it is on the radar of us today. And if you think about it, if you think about, well, why are so many space technologies directly applicable to being on Earth? Well, you're in a spacecraft. You can only use what you brought with you, and you have to reuse that, and your resources are limited. And that's exactly what the Earth is. We're alone. There's nobody coming. The Earth is just a larger spaceship. And so that's
Right.
why all of these things are applicable, because we're trying to keep humans alive with limited resources. Like the
Mhm.
way that they had to scrub carbon dioxide. If we can find a way to scrub it from our environment, all of these things are applicable. And
Right.
if we say, okay, instead of going to the moon, because we know how to do that, we're not going to bring any innovations. Let's say we're going to go to another star. What do we need? And it really doesn't matter if we ever make it there. What matters is the innovation that the attempt will inspire.
Right, right. I mean, innovation, of course, is a main theme of this podcast, but it's really inspiration that drives innovation. So, fueling inspiration, wherever it may come from, I guess, the first order of business, right?
You can't force people to be inspired by heart disease. People are inspired by what they're inspired by. And if
Right.
you take away the inspiration for those minds, you're going to lose something. And so,
Mm,
for years, people were trying to develop an artificial heart, right? And the
hmm
LVAD, the left ventricular assist device, was not functional or working or developed until they talked to NASA engineers who did fluid dynamics. And they were
hmm
able to create the LVAD because of people who were aerospace engineers, right? And so I think the best innovation comes when you have people who love what they do and they're following what they do.
hmm
There are so many people I know who wanted to be astronauts as kids. Like, if you think of all the kids that wanna be actors and wanna be, singers and wanna be entertainers, that's because that's what you see on television. Like,
Right.
I wanted to be an astronaut. I used to see those things on television, and even if I never become an astronaut, I'm in the sciences and engineering today because of that. I know a dozen people who that's their story too. And some of them eventually went on to become astronauts, but some of them, they're in engineering, they're in science, they're in all, and I can't think of any other thing that inspires kids to go on in that way, in that into the STEM fields in the same way that the space program does. And so I'm a huge proponent of the space program, and I think I would love for 100-year Starship to inspire in the same way that NASA inspires.
So you think we'll make it to Mars in the next 10 years or so?
I definitely think we could go back to the moon. Now Mars, like, the changes that happen to the human body in space are completely not understood by the general public. We learn that your body, again, and you're in a this goes back to bone. You're in a microgravity environment, and your bone is like, "What am I here for?" Because most
Right.
of your bones are weight-bearing bones, and you're not bearing any weight because you don't have any more weight. So your bones
Mm.
start to dramatically resorb, right?
Ah,
So
right.
you're at a greater risk for fracture if you get to Mars and you fall down than you would because now you have osteoporosis. But it's a risk that's been identified, right? In addition, so because you're losing all of this bone from being in microgravity, your skeleton is a bank for calcium because calcium is required for all your muscles, including your heart muscle, to function, right? And
Hmm.
therefore, you can't just rely on calcium intake. And this is one of the reasons that people with anorexia have osteoporosis, and sometimes they'll have heart attacks too, because your body is like, I need this calcium, otherwise your muscles will stop functioning. So I'm going to take it from your bones. Right. So if your bones are being resorbed because there's microgravity, there's a lot of calcium in your bloodstream because you take out from the bank, it goes into the blood. And if there's a lot of calcium in your bloodstream, that can affect your muscles, that can affect your kidneys because now your kidneys have to filter it. And when kidneys aren't filtering properly, you can develop a kidney stone, which is all that calcium.
In addition to bone and or organ effects, what about any vascular effects?
Because they're in weightlessness. Now, if you imagine a water balloon, if you hold on to that water balloon, right, it kind of forms a teardrop because all of the water is pooling and the elasticity of the balloon is causing it to pull down like a teardrop. But if that water balloon were weightless, like when you throw it, the elasticity makes it bound into a circle, into a sphere. And the same thing happens when you're up there. So most of your blood on Earth is pooling around in your lower legs. And when you go up into space, it's not pooling down there anymore. It's up towards, it's what they call a headward fluid shift. And because of that shift, your body thinks, because it has all of these receptors, and it thinks, oh, I've got too much fluid. And so it starts to excrete fluid. And so you never see an astronaut returning from space walking, for multiple reasons, but one of them being, you develop orthostatic intolerance because you've eliminated so much blood volume that when you get back to Earth and you stand and your blood pools, you don't have enough in your head to stay conscious. So a lot of you can Google and find, astronauts fainting from this orthostatic intolerance. But,
Hmm.
in addition, we've evolved in the gravity, and we learn to balance in gravity, and there's in our inner ear, gravity receptors that tell
Hmm.
you which way you're facing, and those stop working properly in space. You learn to adjust to not having that input, and then when they come back, they're kinda dizzy, and so all of but the worst thing that we haven't figured out how to mitigate on a trip to Mars is radiation, and there's
Mm.
all kinds of cosmic radiation,
Right.
and people think, "Well, why not just line the spacecraft with lead?"
Right.
And that's not an answer because there are certain kinds of radiation that are more dangerous when they go through lead because they cause secondary ions to come through or secondary
Ah.
electrons.
Hmm.
And, for those, the best thing is acrylic. And so all of these things haven't been fully figured out.
So, just getting back to the gravity dilemma, When you think of sci-fi movies, Star Trek, etc., of course, they have somehow figured out the gravitational problem for space travel. Is anybody working on figuring out how to create an artificial gravitational environment within a spaceship in order to mitigate the deleterious effects of a non-gravity environment on the body?
So there's a couple of I mean, everybody wants to see the rotating spaceship because that's, like, the easiest,
Right. That's
for
what I
the
was thinking.
people, but, it's not easy for the, engineers who have to build that spaceship, because you want stability and all of these kinds of things. So
Uh,
there's, lower body negative pressure suits where you have a suit that, seals at your waist, and it sucks you down and you feel pressure on your
hmm.
feet, so it sucks you into the bottom of that. They have these small centrifuges where you rotate on those for some time, and they're trying to see how much gravity you need. Like, do you need 24/7 gravity? Is it okay to have 10 minutes of gravity a day or simulated gravity? Because being in the small centrifuge, and I mean, like, it's the size of a person, and it's a bed that spins so that you feel, um, as your lower half feels like you're being pushed into the bottom of it. Um, However, like, the people have Coriolis effects, and so they get kinda dizzy, and so you really can't do anything but spin on that thing. Um, and so there is a lot of research into this, into the whether the benefits of those devices,
Hmm.
and but, the jury is still out on those, and, they've been able to mitigate with 4 hours of exercise a day plus diet changes to reduce the salt because salt retention will accelerate bone resorption, but there are places in the body that it's still resorbing, so they've greatly reduced it, but they haven't eliminated the bone loss, and
Gotcha.
then the radiation effects are they can affect your bone as well. And because the space station is still within Earth's magnetosphere, they are still protected, but they get 40 times more radiation than people on Earth, and they
Wow.
wouldn't have any protection on the journey to Mars.
Let me ask you this, Ronke. Many of our listeners are engineers at the very start of their careers. What career advice may you have for these aspiring young innovators?
One of the things that I see young people doing is worrying over making the wrong choice. Like, well, should I do this or should I do that? What if I don't take this class? What if I accept this job? And I've realized because I've been in mechanical engineering, aerospace engineering, biomedical engineering, biomechanics, tissue engineering, my goal at the end of it all was to become an astronaut, and, very few people get selected for an interview, and I wasn't selected for an astronaut. I'm not done trying, but my path just followed what I loved, and I still got to the goal. So if you see, well, what is your goal? Your goal has to be your lighthouse, and there's a bunch of different ways to go along that journey. And so if you just continue to follow what you love doing, and if your goal is to be happy, then that's easy. If your goal is to make a lot of money, then do things that won't impede that goal. If your goal is to be an astronaut, just make sure you have all the requirements that you need. Don't limit yourself. Don't fret over making a mistake because you can't make a mistake if you're doing what you love.
I like that. And finally, Ronke, what do you know now that you wish you knew then?
I wish I knew I didn't have to be an aerospace or astronautical engineer to be an astronaut because I would have just gone straight into biomedical engineering because it's fascinating to me. Um, I just love it, and I wish I had known how wonderful Sabre was from the beginning, because I think I would have had a lot more fun too.
Ronke, I want to thank you so much for spending time with me today and for such a fascinating and inspiring conversation.
Well, thank you for inviting me.
The Innovator Spotlight podcast is brought to you by Johnson & Johnson's R&D Leadership Development Program, cultivating tomorrow's innovation leaders in medical engineering and technologies. I'm Sean Grace. Thanks so much for listening.